Hello, this is Audrey Munger, and this is my Lab 2 for Physics 2212, Magnetic Field of a Bar Magnet. The main goal of this lab experiment is to explore the relationship between distance and magnetic field of a bar magnet. The Biot-Savart law is used to measure the magnetic field of a bar magnet. The observational model from the experiment will be compared to a computational model to see how their magnetic fields differ. In this lab, the system is the magnetometer and the surroundings is the bar magnet. Now looking at some of the main results we got from this lab is we found out there is an inversely related relationship between the distance of the magnetic field and the strength of it. And also the direction of the magnetic field is the same as the direction of the magnetic dipole moment. Now at the bottom of the slide, I have two important equations. The first is the Biot-Savart law. And this law describes the magnetic field generated by a constant electric current. Then I also have the equation for the magnetic dipole moment, which is a combination of the strength and orientation of the magnet that is exerting the magnetic field, which in this case is the bar magnet. Next, looking at the observational model I made, I used a magnetometer app on my phone, a ruler, and a bar magnet all laid out on a flat surface. And then I took measurements of the magnetic fields for the parallel and perpendicular axis of the bar magnet. So on the right side of the slide is all the data I got from the magnetometer app about distance and magnetic field strength. And then the graph on kind of the middle of the slide, that's showing how there's an inverse relationship between the distance and strength because it moves in the negative direction. Now looking at the observation questions, the first one is, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. This is true because, like I said on the previous slide, there's an inverse relationship between distance and magnetic field. The next three questions all go together, discussing as the magnetometer moves closer to the magnet, how the measured x component changes. The first two are false because the fourth one is true. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. That's what I saw from the data I got from mine. Now looking at my computational model, the code in the bottom represents the magnetic field function, which corresponds to the Biot-Savart law, which I showed on a previous slide. The code on top of that is just a snippet of some of the code I used to create the arrows for the magnetic field, which can be seen in the image on the right. There are 6 total arrows, but the code I showed is only showing 2 of them. Finally, looking at the reflection questions for this lab, the first one asks, what if the setup did not compensate for magnetic north and the meter stick was laid out with an angle with respect to Earth's magnetic field and how that would change the results? And I said this would just give the magnetometer incorrect readings that would change the calculation of the magnetic fields because changing the angle will alter both the x and the y component of the magnetic field. The z component wouldn't change because it's all still laid out flat on the table. The second reflection question asks, what if you redid the experiment using 2 identical magnets lined up end to end rather than a single magnet? This would make the magnetic field of both magnets combined together double the magnitude of the magnetic field of just one magnet. And because of the inverse relationship the magnitude of the magnetic field has with distance, this would cause a decrease in the distance of the magnetic field.